In this video, we are going to be running through a numerical analysis example. This one being from section 4.1, page 206, number 9a. But the specific problem is to find the best parabola through the points 0, 0, 1, 3, 2, 3, 5, 6, and compare the root mean squared error with the best line fit. I'm first going to do the line of best fit first, and then actually I'm going to not do a parabola. I'm going to do the best polynomial that would be the best fit, which in this case, since we have 1, 2, 3, 4 points, that would be a cubic polynomial. But at any rate, to first do the line of best fit. So line of best fit. We first need to make a matrix A, but let me underline that. Matrix A. We have the first column being all ones. And since we have 4 points, there would be, well, 4 ones that go along with that. And then all of the x terms. So this would be 0, 1, 2, and 5. In that order. In order to find this line of best fit and, well, the cubic polynomial, or any polynomial for that matter, the equation that we need to solve is A transpose A. A transpose times A, so the transpose of the matrix A times the matrix A is times our solution vector is supposed to be equal to the matrix A transposed times the vector B. And we are trying to solve for this x here. So in order to do that, we first need to, we have our matrix A, we need the transpose. The transpose of A just and changes the columns to be rows. So for the A transpose times A, this would be written as matrices. The first row here would be all ones. And the second row would be 0, 1, 2, and 5. That would then be multiplied by our original matrix A, so 1, 1, 1, 1, and 0, 1, 2, and 5. Doing this multiplication out, we get a lovely 2 by 2 matrix. This would be 4, 8, 8, and 30. For the left-hand side of that equation before utilizing the x inside of there. But that's for that side. For the right-hand side, we need to multiply out, do that right here, A transpose times B. That is going to be, again, this will be 1, 0, 1, 1, 1, 2, 1, 5, times our vector B, which I did not physically write out yet. I should probably do that first. Our vector B is all these y values. So that's going to be 0, 3, 3, and 6. So 0, 3, 3, and 6. When we multiply this, we get another vector. This one will be 12 and 39. So what we are essentially solving from this lovely equation up here, based upon what we obtained here, is going to be this. The matrix 4, 8, 8, 30 times whatever our solution is. I'm just going to use x1 and x2. This is supposed to be equal to what we just got from A transpose times the vector B to be 12 and 39. Mind you, we could just use Gaussian elimination to find that, which is, not particularly bad or terrible to do since we just have a 2 by 2 matrix. But Let me show that in Matlab very quickly. We first need to define our matrix A, so let me do that. A is equal to, we need a bracket. The first row is a 4 and an 8. A semicolon to go to the next row. And let me try to space that correctly. There we go. The second row was 8 and 30. And then we just end the bracket and put a semicolon so it doesn't print it out again. Our vector B, we are going to use a bracket, 12 colon, because we just have the one column, and 39. Again, I'm going to end the bracket, put a semicolon. In order to solve this, I'm going to use the lin solve method, which will solve a linear system of equations. Parentheses are matrix, which is A, and our vector B. That's it. And I almost forgot to close the parenthesis. No semicolon this time. So when we do that, we obtain these two answers of 0.8571 and 1.0714. Since I'm using the online version of Matlab, it automatically rounds to 4 decimal points for both of those. But let me give the actual fractional amounts, since I find those tend to work nicer, especially when attempting to do different parts of this equation. Once we do solve this, we obtain a value for x sub 1 to be 6/7 and x sub 2 to be 15/14, which is what we obtained when we put it inside of Matlab, which means our line of best fit, that looks like this. So I'll call that P of x. This should be equal to 6/7 plus 15/14 times x. And we could see, you know, a rough idea of just how well that actually approximates the data that we have by building a table of sorts, right? So I'll do that here. I'm going to put in our points in these first two columns. We're going to put in the value, and I don't know why I'm going to put f of x when we're using p of x as a notation. Let me fix my notation. And then from that, this is the wrong size. There we go. And then after that, we are then going to calculate the error. So these points were 0, 0, 1, 3, 2, 3, and 5, 6. If we put the x value of 0 into the function, we would obtain an answer of, well, 6/7. Just rounding that as a decimal to 0.8571. If I put 1 into the equation, I get a value of 1.9286. If I put the value of 2 into the equation, I get an exact answer of 3. And if I put 5 into the equation, I get an answer of 6.2143. There are times when we subtract y minus the value of the function. So let me just quickly note that. Y minus the function. We obtain these errors. We have negative 0.8571 for 0 minus 0.8571. For 3 minus 1.9286, we would get 1.0714. 3 minus 3, that makes 0. And 6 minus 6.2143 would give us negative 0.2143. If we were to build the sum of square errors from this, so adding, squaring each one of these and adding them up, we would obtain a value of 1.9284. And then for the mean root square error, this would be the value that we just obtained, 1.9284 divided by 4, all underneath the square root. Toss that into a calculator, you get an answer of 0.6943. So, I mean, it fits between the data, but it doesn't really do that good of a job, right? Look at those error terms that we had. Those are not good. But that's besides the point. That's from that. Again, that's the line of best fit. The parabola best fit, that will give us an answer, but it's not the best solution. The best solution, as I said before, is 1 minus the number of points. We had 4 points. So the polynomial that would fit it the best is actually a cubic. So I'm going to do a cubic. Just to show off what that looks like. Matrix A now, since we're dealing with a cubic. Just took with the line of best fit. The first column is all ones. Second column is all the x values that we had, as we see up here. 0, 1, 2, and 5. The third column, because we're talking about a cubic now, the third column is the square of each of these x values. So 0 squared, that's 0, 1 squared is 1, 2 squared is 4, and 5 squared is 25. The fourth column is going to be all these x values cubed. So 0 cubed is 0, 1 cubed is 1, 2 cubed is 8, and 5 cubed is 125. Doing this one by hand is not the most optimal way of doing it, but, what can you do? That's for matrix A. Our vector B does not change. The vector B is still all those y values. So 0, 3, 3, 6, just like we got up here. So now when we find A transpose A, times A, excuse me, the transpose of this A, so all of these rows become columns and all the columns become rows. This would be the first row of all ones. The next row would be 0, 1, 2, and 5, and 0, 1, 4, 25, and 0, 1, 8, 125. Again, times our matrix A. So this would be 1, 0, 0, 0, 1, 1, 1, 1, 1, 2, 4, 8, and then 1, 5, 25, and 125. Again, as you could probably expect by just looking at those numbers, we are not going to get small numbers when we go through this calculation. I could definitely attest to that. But here we have a 4x4 matrix times another 4x4 matrix. This is, of course, going to give us a 4x4 matrix. And those terms are going to be this. Let me try to give this a nice spacing. This is going to be 4, 8, 30, and 134 in the first column. Second column is going to be 8, 30, 134, and 642. Third column is 30, 134, 642 and 3,158. And our last column, this would be 134 if my handwriting did not just blend in together. Let me actually see if I could just very quickly. Okay, there we go. The last row, so I mean last column, so I don't have to try to squeeze this in. This was 134. Gotta make this legible. 642. 3,158. And you know, this last one's a kind of high. This would be 15,000. 690 for the value of 125 times 125. That's a big giant number, right? So that's for A transpose, the matrix A transpose times the matrix A again. So again, we get that lovely looking matrix there. For us doing A transpose times the vector B, let me just quickly write that out. That calculation is going to be, the first row is all ones, and then 0, 1, 2, 5, 0, 1, 4, 25, and 0, 1, 8, 125. Times of vector B, 0, 3, 3, 6. Doing out that matrix multiplication, matrix times a vector, I mean, we get a vector 12, 39, 165, and 777. And from that, we then need to solve the following system of equations. And certainly, if you thought me doing Matlab for that first example, you know, if you thought, oh, you know, we could just do Gaussian elimination for that, it doesn't take that long. Well, this one would take a lot longer. Let's just say it that way. This will give us a matrix A, the matrix that we got when we multiplied A transpose times A. So let me just very quickly rewrite that. That's 4, 8, 30, and 134. And then 8, 30, 134, and 642. Then we have 30, 134, 642, 3,158, and then finally 134, 642, 3,158, and then 15,690 times our solution vector, which we're trying to find, of x sub 1, x sub 2, x sub 3, and x sub 4. And I did not draw those evenly. There we go. And that is going to be equal to the vector that we just got from the matrix A transpose times the vector B. That was 12, 39, 165, and 777. And again, of course, for this, we're going to get, this time we're just going to get a whole bunch of decimals. They actually round pretty nicely, so we don't have to worry about a loss of significance from this. But just like before, we do need to put in our matrix A. So let me just make sure I have that Oh, nice. And running out. Where do I have it? I have it right there. Okay. So the way that we're going to type this in, since we have a much bigger matrix this time, I'm going to call the matrix A then to be 4, 8, if I don't mistype, 4, 8, 30, 134. A semicolon. And then we have 8, 30, 134, 642. Another semicolon. 30, 134, 642, 3,158. Semicolon. And then finally, 134, 642, 3,158. And let me not do that by accident. And the last term is 15,690. Okay. Our vector B, this was 12, 39, 165, and the last term was, well, last element, use a proper mathematical term, 777. Now when we do that, then solve a matrix A of vector B without the semicolon to make sure we get the answer. We obtain our intercept here is going to be 0, and then we have 5.2, negative 2.55, and 0.35. Going to Matlab here. So let me just bump this back over so we can write that up and look at our error term. So that is going to be, so based upon what we saw there, the value of x, so, I'll write it over here. X sub 1 was 0. We don't need that term at all. X sub 2 was 5.2. X sub 3 was negative 2.55. And X sub 4 is 0.35. So, because of that, the polynomial, the cubic polynomial of best fit that we have, I'm going to denote that as P sub 3 of x. That is 5.2 times x. Now note, because x sub 1 is 0, I am not going to bother writing that in the formula, since we don't have an intercept. 5.2 times x minus 2.55x squared plus 0.35x cubed. Now, there's going to be something very nice when we look at the error terms for this, but let me just scroll that down a little bit more so I have some room to write that. So the table that we're going to make. Again, we're going to have the values from the points x and y. We're going to use the values from our cubic polynomial of best fit, which will be the best fit, and of course the error terms, which once again the error will be calculated as taking the y values minus whatever the predicted values are from our equation. The points that we had were 0, 0, 1, 3, 2, 3, and then 5, 6. If we plug 0 into our polynomial, we get a value of 0. If we plug 1 in, we get a value of 3. Plug 2 in, we also get a value of 3. And we plug in 5, we get a value of 6. Which means when we subtract these now, all these error terms are all 0. So the sum of squared errors again, we just add these up. We square each one and then add them up. You'd get a value of 0. For the mean root square error, this would be the square root of 0 divided by 4. Since there's a 0 in there, this is just automatically 0, which means we can see from the calculation that we have here, this cubic polynomial is indeed the best fit because we get the exact values of the points from our equation. Do note, however, that if we try to use the function, and I'll write it here so we can note it. It was the I think it was polyval, right? Let me check that. Excuse me, not polyval. Well, polyval can be used. It's the polyfit function. If we use polyfit in Matlab to do this, it would actually run an interpolation for this. It would not give us this particular polynomial, unless it so happens to equal the same exact thing. It may not. But doing it this way, we obtain the exact approximation for it. So because of that, we are not using that in Matlab. What we did was good enough to find out our solution. And because these were nice terms to begin with, we didn't have to worry about any potential loss of significance. Let me know if you have any questions or concerns. Thank you.